All right, let's take a look at page 152. We are going to continue talking about graphical characteristics today, and today's the day where we're going to bring all these characteristics together and try to identify any little property we can about one graph. So you're going to see like domain and range, above x-axis, below x-axis, all these different properties that we've been talking about kind of since day one. Okay, we're going to bring everything together today. Before we get there, though, we do need to talk about one more thing related to the point of inflection characteristic that we were kind of introduced to yesterday. Once we find the points of inflection where the curvature of the graph changes, we can then use those to help us identify the intervals of concavity. So we can actually describe where the graph is concave up. Okay, it kind of looks like a regular parabola shape, but then we can also describe where it's concave down, okay, where it's kind of that umbrella shape to it. So by definition, we'll just say intervals of concavity are intervals on the graph that describe concave up or down sections. So we're going to take a look at two graph examples to help us identify these intervals. And these two graphs are actually the same ones that we did yesterday, that we practiced identifying the points of inflection. Can you do me a favor, just because I don't have it available with me right now, can we flip to the previous page to look at this example? And can someone tell me where the point of inflection was? Where are you supposed to be right now?
Study hall.
Study hall? Yeah.
No. Yeah, 2-2. Let's think this graph. No.
You just owe me one for this.
Yeah.
Do you have a calculator?
She's like, it's instead of a multiplicity of 3, and then goes, yes, and she goes, no.
There's one in the back here. All right, where was our point of inflection from yesterday? 2, okay, somewhere right there. All right, x equal, we'll go this way instead. X equals 2. What about this other shape? This other graph? Where were the points of inflection from yesterday? -2, 0. Okay, so x value of -2. And where was the other one? -0.5, comma something? Can we find these from yesterday? Yeah, it's the last two graphs on the previous page. Can we find them? Okay, we just don't want to talk today. That's going to change. Take a look. So these are the points of inflection. These are where the curvature of the graph is changing. So if we were to start to trace the graph, maybe we'll do the first one. If we start to trace the graph, and then we have to stop at the point of inflection because that's where the curvature is changing, notice how this initial section that I traced looks like an upside down parabola. So we're going to classify this as concave down. I'll abbreviate CC for concave. So concave down, and if we write the interval, notice how, since we have an arrow, we can go forever to the left, okay, -infinity, and if we stop at the point of inflection, we're going to have to stop at the x value of 2. If I continue to trace the graph, I do not have another point of inflection to stop at. So this is the last interval that we're going to write. And this second interval looks like a regular parabola. So we're going to classify that as concave up. So that section started at the point of inflection at 2. And if we can go on forever to the right, we'll go towards positive infinity. So once you identify the points of inflection, we're going to trace the graph to identify the curvature. Is it concave up or is it concave down? Let's try the next one. We already have the points of inflection. If we trace the graph and stop at a point of inflection, how would you classify this curvature? Does it open up or open down? Up. Concave up. Notice how it kind of looks like half of a regular parabola if you were to trace the other side. So concave up. That interval, negative infinity, and we stopped at the point of inflection at -2. If we continue to trace, I'll have to stop at the next point of inflection, and this little interval looks like an upside down parabola, just maybe half of it. So we'll label this as a concave down interval. That goes from -2 to the next point of inflection of -1/2. And if I continue to trace, I do not have another point of inflection, so this is going to be our last interval. Notice how this last section is concave up. It looks like a regular parabola. So we're going to throw in a U, like we typically do when we have more than one interval to write. And this interval is going to go from -1/2 to infinity. Why do you think I was using parentheses on those values instead of brackets? What do you think, Julia? It's not direction, it's a change in curvature. Okay, change in direction are like the high points and low points, but you had the right idea. Okay, so since these are points of inflection, that's where the curvature is changing. So you cannot classify it as up or down because it's changing at that spot. It's not just up or just down. So we're going to go ahead and use parentheses for those values. Does that make sense? Do you think we can do that? Okay, so we practiced finding points of inflection yesterday. Once we find them, we can then classify the curvature, concave up or concave down. All right, so without further ado, we're going to bring all these different characteristics together and try to identify any property we can about a polynomial graph. So we're going to do this first one together, and then I'll let you do the other one on your own just to see how we can handle it. But we're going to go through all these different properties related to this one graph. So some of these are definitely going to be throwback. Domain. How far left and right can this graph go? Maybe trace it with your pencil. Any holes, asymptotes, missing sections that we have to worry about? No, so what's our domain? Negative infinity to positive infinity. All real numbers. What about range? We'll drag low to high. Yeah. There we go. All real numbers again. All right, zeros and their multiplicities. So can we find the x-intercepts? And then based on the way the graph looks at those spots, we should be able to determine their multiplicities. Can we find some x-intercepts? -2, 1, 3. What about their multiplicities? Good, Hadley? They're all 1. How'd you know? Straight through. Okay, so I'm just going to go ahead. I don't care how you label the multiplicities. You can do arrows. You can write m equals, like m for multiplicity, not for slope, okay, but m for multiplicity. I'll use parentheses, but notice how at those spots the graph goes straight through. Multiplicity of 1. All right, what about intervals where f of x is greater than 0? Can we think of the characteristic that we're trying to identify from that notation? Yeah.
Above the x-axis.
above x-axis. All right, so can we list those intervals where that characteristic happens? You want to keep going, Lainey? Go ahead.
-2 and in parentheses.
Okay.
1, and then 3 to infinity.
Can you, so you said parenthesis for -2,
And in parentheses for 1, in parentheses for 3,
and infinity. Good. Okay, so we're above the x-axis in these sections. We cannot count the x-intercepts because we're on the x-axis at those spots, and we strictly just want to be above. So parentheses, we cannot include those. The next one, very similar. We're just going to find where we are below the x-axis. So based off the graph, that's kind of the other intervals that we haven't listed yet. -infinity to -2, and then 1 to 3. All right, let's take a look at left end behavior. So as the x's get very, very negative, okay, as the graph goes to the left, how are the y values of the graph behaving? Are they going up? Are they going down? What's happening on the left-hand side? They're going down, okay, so -infinity. If we look at the right-hand side, that means the x's are getting very, very large. So as the graph goes to the right, notice how it will also go up. So the y values are getting larger, okay, positive infinity. We doing okay so far? All right, we're kind of bringing everything together, full circle. What about the type of function? Can we name this graph? Yeah? Why? Uh-huh.
because the multiplicity is algebra.
All right, multiplicities, I'll abbreviate multi, add, 2, 3. Good. So we kind of had to use a previous characteristic to help us with that. 1 plus 1 plus 1, we got 3, so we're cubic. All right, intervals where f of x is increasing. So if you were to physically walk along the path of this graph, where would you be walking up? Any ideas? I'll start things off. -infinity to -1. Okay, so this interval. Is there another place? Yeah, we have 2 to infinity. All right, this interval. Good. Decreasing, where you'd be walking down based off the graph that looks like our middle section. So we're trapped between -1 and 2. Okay. Why are these parentheses and not brackets? Why can we not count that high point and low point? Yeah? They're changing spots. Okay, so you are not increasing here, you are not decreasing here, you are changing the way you are moving. So we cannot count that as an increasing or a decreasing spot. Okay, kind of similar to, what was the other one? Oh, we did up here with the concavity. Okay, I had to go back for a little bit. All right, what about maxes and mins? So we talked about these yesterday. We kind of had two different types. We had to look at relative versus absolute. So relative maximums were the ordered pairs, the points on the graph that have a high value. So we're looking for high points or like the top of a hill, the top of a mountain. So can we find a high point on our graph? You can also think about it as changing from increasing to decreasing. That's what actually creates the high point. Go to Olivia. -1, 5. Good. I think that's the only one that fits that definition. Very similar, a relative min, we're looking for a low point on the graph, so something that changes decreasing to increasing. Good, Hadley? Not Hadley. Alicia, sorry. 2, -2. Good. And I think that's the only one. All right, so relative maxes and mins are points, and we're just looking for any high point or any low point. Okay, as long as it's at the top of a hill or the bottom of a valley, we can classify those. Absolute, on the other hand, are the highest point or y value or the lowest point or y value. So we're looking for the highest and lowest heights. How high does this graph go? Infinity. Will you ever reach that? You'll never reach that height. Okay, so we do not have an absolute max. It's going to go on forever. Okay, because we have that arrow going up. What about the absolute minimum? None. Okay, kind of the same reason. We'll never ever reach negative infinity, so there's no lowest value. It goes on forever. Looks good. All right, something else, a characteristic-wise that we talked about yesterday were the points of inflection. And there were 3 places that we had to keep in mind where these changes in curvature could happen. Can we kind of review those 3 different spots? If you got a flip, you can look. Go to Hadley.
There's a multiplicity of 3.
Multiplicity of 3.
Approximately the midpoint of the max or min.
We got to look for the middle of a max or a min.
Or approximately the midpoint of the multiplicity of 3 and the closest max or min.
Okay, so it's kind of a merger of the previous 2. Okay, so we have 3 possibilities. Looking at this graph, do we have a multiplicity of 3? No. So, because we labeled them over here as 1. So if we don't have a multiplicity of 3, we can automatically rule out the other option because that involved a multiplicity of 3 as well. So we definitely need to check out, though, do we have any maxes or mins, any high points and low points? Yep, and we check those out here. Okay, so we have a maximum, a relative max of -1, 5, and a relative min of 2, -2. So we need to find the middle of those 2 points. All right, so if you looked at a number line, what's the middle of -1 and 2? One half, okay. All right, and then if you were to look on a number line, what would be the exact middle of 5 and -2? Bless you.
Thank you. Goes once in.
Can we find it? Mm-hmm. 1/2. All right, so if we were to plot this point on the graph, we'd be somewhere right here. And that pretty darn looks close to the middle of the high point and low point, right? Approximately, roughly. I say that's good. Okay, so there's our point of inflection. Now that we have that, we can trace the graph to determine where we concave up and concave down. So if you start to trace the graph and you stop at a point of inflection, because that's where the curvature is going to change, it looks like our initial section is upside down parabola shape to it. So we'll label that in the concave down box. We'll have negative infinity, and we stop at the point of inflection, which has an x value of 1/2. If we continue to trace, we do not have another point of inflection, so this is going to be our last interval. Notice how it looks like a regular parabola shape opening up. So that would go from 1/2 to positive infinity. How are we doing with bringing everything together? It's a little iffy because it can be overwhelming. We have all these different properties, characteristics that we've been talking about, but we can apply those to any graph we have. So what I want you to do is on the next page, try to figure out those properties for the other graph, and then we'll check them out in a little bit.
No. So, well, this is a possible equation based off of the x-intercepts, right? You might have some multiplier out front that's like stretching the graph somehow to make it look like this. We have no idea like how to figure that out right now. We'll get there eventually. But this is a possible equation based off of it.
Can we just leave it in this one or this one?
Notice how I didn't say find that equation like that. That's a different than possible.
Is multiplying it out.
Yeah. No, you can leave it in factor form.
It's like, we can get up to like the fifth.
Yeah, it's sweet crazy. Yeah. Oh, I think
Isn't increasing at -3?
Yeah, it's constant. Yeah, I'm pretty sure it's not. No, it's not.
No, because
It's not constant. It's only on that 1.1 side.
yeah,
So it is still increasing, just very slightly.
Okay, so I guess then it would be 3 and then 2, 5, 8, or 0.
Yeah. Sometimes they're sideways. Yeah. Just slightly sideways. And then other times it's actual.
-3 zeros are relative to this one, right?
And now, I'm looking forward to looking at
That's a good one.
the crap's on you.
This one
Dude, there's an
I
entire
don't think it's qualified as anything.
on YouTube. There's an entire there's an entire there's like 3 entire episodes of the course that you did on because there was like a series. Or it was like, you know, it was a marathon or something. Yeah. Where it was like
What's halfway between?
it was a 3-part episode or whatever. And like in the 3 total episodes. I was about to.
All right, it kind of looks like we're good to go. If you're still working, that's okay. We'll go ahead and start, and then you can check them as we go. Matt, pick a characteristic for us.
Characteristic.
Yep, any one. What'd you get? Pick one.
Domain.
Domain. What's a domain?
Negative infinity to negative infinity, or to positive infinity. Oops.
Looks good.
Oops.
All right. Grace, pick one.
For the range, I got -infinity to 6 times a factor.
Looks good. All right. Travis, pick one.
How about absolute maximums?
Absolute max. Go ahead.
6.
Y equals 6. Okay, so absolute maximum is the highest height. You do not have to write an ordered pair. I noticed how walking around some of you did that. Okay, it's the highest height. A Y value. Looks good. Blake, go ahead and pick one.
The relative minimum is y equals 0.
Relative. Okay, so relative is a point.
-2, 0.
-2, 0. All right, so this one right there. Looks good. Erica.
Absolute minimum.
Okay. Why?
Because you can't reach negative.
Yep, we're going to go down forever, so there's no lowest height. Mason, go ahead and pick one.
Zeros and their multiplicities.
All right.
-5, -2, and then 2 are zeros, and then -5 has a multiplicity of 1.
Yep.
-2 has a multiplicity of 2, and then 2 has a multiplicity of 1.
Perfect. All right, so we go straight through for -5 and 2, and then we bounce at -2. Looking good. Elsie, go ahead and pick one.
Left infinity.
Okay.
So
All right, so on the left-hand side, the graph is going down. So y values are approaching negative infinity. Jack, go ahead and pick one. Say it again.
Sorry.
It's okay.
Points of inflection.
Ooh, go ahead.
Just the curve.
You can pick any one you want.
That was wrong. Just wait.
Okay.
3 and 1.5.
Are we doing the points of inflection?
Yeah.
Okay, 3 and
1.5.
1.5.
Negative 3, sorry.
Negative 3, okay.
And negative 5. Negative 0.5, 3.
Negative 0.5 and 3, okay. Can you tell us how you got those? Like, of the 3 methods that, or 3 things we have to look for, which ones did you use for those?
Number line.
The number line? Okay, so what points were you looking for on the graph to help you get those? So how'd you use your number line? Negative 4, 3. Okay, so we have a maximum and a minimum. And we'll find the middle of those. So using a number line, the middle of negative 4 and negative 2 is negative 3. The middle of 3 and 0 is 1.5. So graphically, we're somewhere right there. Okay, how'd you get the next one? Same thing. All right, so negative 2 and 0, and the other high point 1 and 6. All right, so the middle of negative 2 and 1 is negative 0.5, and the middle of 0 and 6 is 3. So negative 0.5, comma 3, somewhere right there. Looking good. How are we doing so far? We got to go over any of those a little bit more? No? All right. Alicia, whatever one you want.
I have a function and y.
Go ahead.
It is a quartic function because the multiplicity is out.
There we go. Because multis add to 4. All right. 2 plus 1 plus 1. Good to go there. Hadley.
How would you write the nth?
Sure.
So as x approaches positive infinity, y is going to go to negative infinity.
There we go. The right-hand side goes down. Noah's not here. Blair, go ahead and pick one.
Intervals of x where f(x) is greater than 0.
Go ahead.
-5, -2, both parentheses.
Okay.
2, and then -2, 2, both parentheses.
All right. And what characteristic were you identifying there?
Where it's above the x-axis.
There we go. Above x-axis. Looks good. Lincoln, go ahead and pick one.
So the intervals of the x values were when f of x is less than 0,
Okay, go ahead.
negative infinity to negative 5,
Okay.
and then 2 to infinity.
2 to infinity. And what were you finding there?
The when f of x was less than 0.
Less than
below
0?
the x-axis.
There we go. Below x-axis. Perfect. Caitlin's not here. Julia, go ahead and pick one. Increasing? Okay. Yep. Positive what? Did you say? Okay. I think you said 6 and you were just looking there accidentally. Okay. Looks good. Lainey.
I'll do intervals where f of x is decreasing.
Decreasing? Go ahead.
And I have negative 4 to 2.
To what?
Negative 2.
-2? Okay.
U, 6, and 1.
Okay.
And to negative infinity.
Negative infinity? Okay. I think you said negative because it's going down, but if we're going from 1 to the right, it'd be positive infinity? Okay, because we're traveling that way. Looking at the x-axis. All right, Logan, go ahead and pick one.
The relative max
Relative max, go ahead. Negative 4, 3. Okay, so that's a high point on our graph, definitely. And 1, 6. You had 2 of them. Okay, you had 2 high points on the graph. Maggie.
I'll do intervals where it's concave down.
Down, go ahead.
Negative 30 to negative 30, negative 1/2 to negative.
All right, so maybe we'll label those on the graph. So intervals of concavity, we got to pay attention to those points of inflection. So Maggie said negative infinity to negative 3. That's this interval. Notice how it's an upside down U, fits that description. And then negative 1/2 to infinity. Looks like we have an upside down U as well. Looks good. Lizzie, last one.
The concave up would be -3 to -0.5.
Negative 3 to what? Negative 0.5? Okay, negative 1/2. Good. So interval, the last one left here, between the points of inflection. Notice how it's a regular parabola going up. How do we do? Good?
Great.
Good job, guys. All right, we'll stop there for today, and we're going to go ahead and look at the next section tomorrow. One second.
Actually, I got 2 well, actually, 3